Hey, welcome to Real Analysis. In this first video lecture, we're going to introduce our topic of study, that is analysis of functions of real numbers, by looking at a careful treatment, or at least discussing a careful treatment of the real number system. Um, Real analysis, which is really sort of a careful look at the topics that you learned in calculus, topics like continuity, limits, derivatives, integrals. They're all sort of based on intrinsic properties of the real numbers. Maybe you remember a lot of times in your calculus courses, the book or the instructor would say something like, oh, we're not going to prove this. It's beyond the scope of the course. And typically speaking, it was beyond the scope of the course because there wasn't sufficient development, careful development of the real number system over which all these functions and these notions are defined. And so our purpose in this course is to prove that stuff. So we do have to kind of carefully develop this real number system. Um, a rigorous development of the real number system is almost a course in and of itself. To sort of start with the counting numbers, the natural numbers, and work your way up to an axiomatic description of the set of all real numbers is sort of a time-consuming and laborious task. It's a task that I don't really want to start our course with here, but I do want to develop the course material with rigor and precision. So we have to have some agreement about what our fundamental tools or axioms are going to be. So the first few sections of chapter 1 in our text is sort of a listing of what those axioms are. And I also want to try to give you a spirit of what it's like to sort of derive some of these well-known things from elementary principles. So having said all that, I don't want you to lose sight of the fact that we are still talking about real numbers. You can visualize the real numbers. Don't throw your intuition out in the course. The real numbers are visualized along a line. You know what I mean by less than or equal to, and so on in the real number system. So don't chuck out all of your intuition and experience that you have with working with these numbers as we start our course, but do try to get kind of in the axiomatic spirit of like, well, how would you derive some of these things from elementary principles? As you can see, you'll see here in the last part of this short video lecture that deriving some otherwise obvious looking facts, well, sometimes it's not all that easy to do from a limited set of axioms. Okay, but it can be challenging but fun. Okay, so that's kind of what we're off to do here. So let's start off in the section 1.1 is just sort of that brief introduction. I hope you read it. I picked this book. It's very readable. The style of it is sort of a narration style. It's not kind of a terse, intimidating book. So I hope you're going to get in the habit of kind of thoroughly reading these sections as we cover them. So section 1.2 introduces the real numbers, or rather the axioms that we'll use, or the real number system itself. We'll start from the kind of beginning, the natural numbers. We can give a set theoretic description of the natural numbers. What do I mean by the set of natural numbers? I mean the positive counting numbers, 1, 2, 3, 4, and so on. And we'll use this familiar sort of blackboard font, people call it, the letter N, to denote the set of natural numbers. Okay, so the dot, dot, dots certainly indicate that it's an infinite set. All right. Slightly bigger set, the set of integers. Well, it contains the natural numbers, contains all of those positive counting numbers, but the integers also contain the number 0, together with the additive inverses, the negatives of all the natural numbers. That's what we're going to denote by the set of integers, using, again, the familiar kind of blackboard font, Z. The German word for Z starts, or for whole number rather, starts with the letter Z. So that's where the notation comes from. Okay, rational numbers, I can give a set theoretic description of them. Rational numbers are the set of all ratios of integers where the integer in the denominator is forbidden to be 0. Okay, so it's a set of all fractions of integers with non-zero denominators are the rational numbers. And you know from experience that two different ratios of integers can be the same, right? The rational number 1/2 and the rational number 2/4 are the same. So there's sort of an equivalence relation on the set of these pairs of integers. We will skip over the details and just kind of use our intuition and experience with these. All three of these sets of numbers have operations of addition and multiplication. You can multiply and add natural numbers, integers, rational numbers, always yielding numbers of the same kind. And they also all have a notion of order, right? You can, given two natural numbers, you can decide if one is bigger than the other or bigger than or equal to the other. Same for the integers, same for the rational numbers. In fact, these sets live inside of each other. Every natural number is an integer by definition. If you're willing to associate the integer a with the rational number a over 1, we can see that every integer is itself a rational number, right? So those things we can kind of give explicit set theoretic descriptions of, but not the set of real numbers, right? It's not possible for me to write down in some simple way anyway what the set of real numbers is, say building it off of the set of rationals. If you read in the book, the author gives a couple of ideas. You can talk about decimal expansions and so on. And the rigorous development of the set of real numbers is again the part that we're going to kind of skip over instead of starting off our course with that foundational topic of the construction of the real numbers. We're just going to kind of take them for granted. We're going to axiomatically specify them. So we're going to say that the real numbers are a complete ordered field that's bigger than or equal to or contains the set of rational numbers. It's some set that goes at the end of our chain up here. So I'm just going to kind of impose that this set R is a set that contains all of those previous sets of numbers and then some. And then I'm going to specify some axioms that we can use to develop further properties about these numbers, well, and eventually functions of these numbers and limits and so on. Okay. So what are these axioms? Well, there's sort of some algebraic ones, the so-called field axioms. That tell us sort of about the multiplication and addition structure in the real numbers. And then there's a different set of axioms that will tell us about the order. So section 1.3 in our book is these algebraic operations, or these so-called field axioms. Okay, so the algebraic structure that we're describing here is called a field, but you can just think of this as the algebraic axioms of these numbers, that is the rules about how to multiply and add them. Okay, so we're going to suppose, and again, don't forget, you know what the set of real numbers is, so you don't have to be in the mindset that you don't know what I'm talking about here. You know what the set of real numbers is. I'm just listing a specific set of axioms, assumptions, things that we won't prove, but we'll assume, and then from them we'll derive all of the properties that we need about these numbers. Okay, so we're going to say that the real numbers come endowed with two operations. One of them is called addition, denoted with the usual plus, and one of them is called multiplication, which we typically just denote by writing the two numbers next to each other like usual. So AB means A multiplied by B. And then these things satisfy these field axioms. There's 9 of them. Okay, so the author has enumerated, and then let's look at the first 4, A1 through A4. The A is sort of for addition. All right, so these 4 axioms. A1 is that this addition operation is commutative, that for any 2 real numbers, the sum is a real number, A plus B, and A plus B is equal to B plus A. So it's not something we're going to derive, but we'll just assume it. The second axiom, A2, is the so-called associativity axiom. Okay, so that if you take 3 real numbers and add them together, grouping in the 2 possible ways, you always get the same thing. So these things, their names, if I write them out here as we're talking, this is called the commutativity axiom. The operation of addition is commutative. This one's called the associative axiom, associativity. Okay, third axiom is we're going to assume that there's an additive identity. So there's a unique element of the real numbers that we'll denote by 0. And when you add any real number to 0, you get that real number back. Okay, so that's called the additive identity. Okay, and the fourth and final algebraic, or excuse me, addition axiom for this is that for any real number A, there's some real number called negative A, or the additive inverse of A, that when you add it to A, you get the 0 element. Okay, and we're also going to suppose that that number, no, it's actually, we can derive it actually. So there's a corresponding number denoted by minus A, and from the above axioms, we could derive that minus A is actually unique given A. Okay, so that's called the additive inverse. So these are the 4 things that we're going to assume about the addition. of real numbers. All four, I think, very familiar properties. We're just going to assume them as axioms. Okay, likewise, there's four multiplication axioms. There's four multiplication axioms. They're kind of the same in some sense. So the first multiplication axiom says that the product of two real numbers is real, and again, is commutative. Okay, so there's a commutativity for multiplication. The second one is associativity for multiplication. That when we multiply real numbers, grouping three real numbers grouped in the two possible ways, we always get the same result. So an associativity for multiplication. The third one is the multiplicative identity. There's a real number called 1 that when you multiply any other real number by it, you get that real number back. Okay, and we're assuming it's unique. And then the last one is sort of the multiplicative inverse. The only real number that doesn't have one is 0. So for any non-zero real number, there's a corresponding number denoted by a to the minus 1. I'll also call it the inverse, but to emphasize it, I'll call it the multiplicative inverse. And it has the property that when you multiply it by a, you get 1. Okay, and I'm going to kind of spontaneously throw this as an informal exercise. You can show that given a in the real numbers, that minus a and a to the minus 1, if a is not 0, are unique. So in other words, a to the minus 1 is the only real number that you can multiply by a to get 1. Okay, it follows you can show that they're unique. So every real number has a unique additive inverse. Every non-zero real number has a unique multiplicative inverse. Cool. And these things are, again, I hope, sort of familiar. And then the ninth and final field axiom, the author calls it AM1 because it's sort of about addition and multiplication. Well, it relates them. It's the distributive law. So for any three real numbers, the sum of a and b times c can be written as the sum of a times c and b plus b times c. Okay, so that kind of relates the addition and multiplication operation. So those 9 axioms together, if you're in the abstract algebra class, you'll study this kind of abstractly. Any set with two operations that satisfy those 9 axioms is called a field. So in particular, the set of real numbers is a field, and we'll just call it the field of real numbers. Again, kind of an informal axiom. You can show that if you restricted yourself to just say rational numbers, the rational numbers also satisfy those things. They satisfy these field axioms. Let me just write it like that. Z and N don't. You can find at least one, probably more than one, of those field axioms that the set of integers and natural numbers under addition and multiplication will not satisfy. So the real numbers, the rational numbers are fields. They satisfy the field axioms. The natural numbers and the integers are not fields. Okay, they're sets with addition and multiplication, but the addition and multiplication structure is not sufficiently rich in order to make the set be a field. Okay, cool. Moving along here, the fourth section of our chapter, the last one I'll talk about in this video lecture, brings in the notion of order or size into the real numbers. There's 4 order axioms. Again, don't lose sight of your intuition. You know what less than or equal to means on the real line, and we'll use that geometry in your intuition. But to be more precise, the first order axiom, O1, says that if you give me 2 real numbers, exactly one of those 3 numbers or statements is true. The 2 numbers are either equal, A and B are the same, or A is less than B, or B is less than A. Exactly one of those 3 things is true. Okay. The second one is kind of a transitivity axiom, if you like. For any 3 numbers, A, B, and C in the real numbers, if A is less than B and B is less than C, then A is less than C. So we're going to assume that as an axiom about this order. The third one kind of relates order in addition. If you take 2 numbers A and B, say A is less than B, then for any number C, A plus C will be less than B plus C. You can add any number to both sides of that inequality. Okay, that's true for any number C. And then the fourth one is kind of an analogous thing for multiplication, except the value of C has to be positive to preserve the inequality. Okay, so those are the four axioms. You know tons of other properties about order, right? And addition and multiplication. And all of those other properties that you're thinking about, they can be derived from these minimal set of axioms, the 9 field axioms together with the 4 order axioms. So 13 total axioms. We can derive everything we need to know about the set of real numbers. And this is kind of how we'll lay our foundation, is we're going to just assume that this set of real numbers exists. It satisfies these 13 axioms, and we'll go from there. Okay, so that's how we're going to begin our course. I'm going to end this lecture just kind of giving you a little bit of a sample of what I mean by that. Like, for example, one thing that you know as well as I do is that when you multiply any real number by 0, you get 0. 0 being the additive identity, right? Anything times 0 is 0. You know it as well as I do, although it was not one of our axioms. Our axioms never specified that, so we can derive it. So let me give you an example of how to derive it. If you take, say, a real number called a, and you look at 0 times a, well, I just kind of tried to highlight here using the third addition axiom. 0 is 0 plus itself. So I'm replacing 0 with 0 plus itself, and then using the distributive law, the axiom AM1 in our book, I can write that as 0a plus 0a, right? So then I take that equation and I add the additive inverse of 0a to both sides. That thing exists by the axiom A4. And then if you like, here I've got these parentheses on the the right-hand side of this thing. The axiom A2 says that I can reassociate those parentheses. I can rewrite this side like that, right? But then on both sides, the 0a plus its inverse is 0. So I'm left with 0 on the left-hand side. And if you like, I get 0 times a plus 0 over here, but that's 0 times a. All right, so I'm just giving you an example of how to illustrate this from the axiom. So what have I concluded? I've concluded that 0 times a is 0 for any a. All right, so that's not something I have to assume. I can derive it. Okay, so I've listed here some other things that just kind of came to mind as I was putting these lectures together. I don't mean that this list is inclusive or it doesn't include all possible examples, but I was just trying to think of some other kind of obviousisms that aren't listed in our axioms. You can derive them all. So for example, what's the first one I wrote here? If you take the additive inverse of 1 and multiply it by a, you get the additive inverse of a. You can derive that from our axioms. Negative 1 times a is negative a. Another one, the additive inverse of the additive inverse of something is the something. Negative negative a is a. You can show from our axioms above that if a is greater than 0, then its additive inverse is less than 0. All right, you can show, believe it or not, this isn't an assumption that we have to make, you can derive from our axioms that the real number 1, the multiplicative identity, has to be greater than the additive identity. Okay, or another one, that the square by definition, meaning a number times itself, of any real number is always greater than or equal to 0, and it's equal to 0 if and only if the number is equal to 0. These are all things that you can derive from the axioms. I hope you stop the video and try to derive some of them. It's fun. They're not always completely easy. You kind of have to spin around a little bit, and what you want to make sure is that you're kind of deducing things not based on stuff that isn't proved. So if you want to take this challenge, you want to try to show those things using only the axioms. Well, using only axioms and things that we've deduced. Right? Because once you deduce something from the axioms, then that's in play. You can use it to derive further results. You don't always have to reinvent the wheel. Okay, so I think I'm going to end this video lecture by proving one of these things that I listed up there, that if you take a real number and it's greater than 0, then its additive inverse is less than 0. Okay, I'm going to try to kind of walk you through an axiomatic based proof of that fact. So I kind of sketched this proof somewhat informally here, but let me try to kind of annotate it with some details. So I want to try to show, my eye on the prize is that this number minus a, the additive inverse of a, is less than 0. I've got an order axiom that says every real number, including minus a, well, it's either less than 0, it's equal to 0, or it's greater than 0. All right, every real number has to be in exactly one of those three categories. So the first part of my proof is I'm ruling out the fact that it equals 0. So I'm going to be looking for a contradiction. If minus a equals 0, I'm borrowing an unproved fact here that then its opposite would equal the additive inverse of 0. Okay, but you can derive this from the axioms. Negative negative a is a, and you can also derive from the axioms that negative 0 is 0. So my statement is that if the opposite of a is 0, then a is 0, right? But I'm assuming that a isn't 0. So therefore neither is its opposite. Okay. All right. And now to prove this, if a is greater than 0, then using the third order axiom, I can add the opposite of a to both sides of that inequality. But a plus its opposite is 0, and 0 plus the opposite of a is the opposite of a. So there you go. If a is greater than 0, then its opposite is less than 0, right? And by the way, we'll freely use that in our notation. If I write this, I could also freely write negative a is less than 0. It's the same. Okay, anytime one thing is less than another, then you can also write that as a greater than statement. Cool. All right. So just to kind of prod you one more time, see if you can derive any of the following facts. There's some written above. I've even repeated one. You can derive that 1 is greater than 0. If you take 4 positive numbers, say a less than b and c less than d, then the inequalities multiply. Any numbers that satisfy those add. If the product of two things is positive, either both things are positive or both things are negative. These are all super familiar facts. I try to derive them from the axioms. Maybe we can talk about some of them in the class meeting. Last one I'll mention here is that if you take positive numbers, one is less than the other if and only if the squares satisfy the same. Assuming for a second that every positive real number has a square root, we could also throw in here that this is equivalent to the square root of a being the square root of b, where what is the square root of a? The square root of a is a number whose square is a. Again, why would such a thing exist? Well, we'll have to work a little bit further in the future to prove the existence of it. All right. So as we get started, the last thing I'll say in this lecture, we're at the 28-minute mark here, is or 29-minute mark, is that we're going to try in our real analysis class to rigorously establish all of those facts from the first semester of calculus that you learned. And in order to do that, we have to be a little bit more careful than we were in a calculus class. And for the most part, that carefulness will mean that we need to be much more precise about properties of the real numbers that we're going to use. Some of those properties are so foundational and take so much time to develop that we're just going to assume them. So starting off in chapter 1 here, so far we've talked about sections 1.1 through 1.4. The author is trying to carefully lay out for us what are our assumptions, our axioms, what are the things that we're deriving from them. Okay, thanks for your attention.